Let's talk about the preparation of epoxides. There are three main ways that you can prepare epoxides as presented in the Klein's textbook. We can use peroxyacids. We can make the the bromohydrin or chlorohydrin and then react it with base. Or we can do a Sharpless asymmetric epoxidation. Now, peroxyacids are acids that look a lot like a peroxide. So, for example, this is called peroxyacetic acid because it looks a lot like acetic acid, but it has an extra oxygen in there, okay? And the more stable solid substance that's used for this is metachloroperoxybenzoic acid, which has this molecular formula, this structure. And since it's a solid, it's more easily stable. It can be recrystallized or transported, and it's harder to spill a solid than a liquid. I would say it's easier to clean up, definitely. So this is mCPBA. Okay, we use small m there because it's a meta isomer in a benzene compound, and we'll talk more about that later. So this stands for metachloroperoxybenzoic acid. And benzoic acid looks like this, so it's a little bit similar, except you have a chlorine in there and an extra oxygen as well. So these are oxidizing reagents. In one fell swoop, you can transform an epoxide, an alkene to the epoxide, and it happens through a syn addition. So if you treat this with mCPBA, you form the cis epoxide in this case. Okay. All right. So this is a syn addition of oxygen across the two carbons of that alkene. If we have a molecule that looks like this, and we treat this with mCPBA, let me just point out that this molecule is a cis isomer. And when we get the epoxide, there's different ways of drawing this. I will choose to draw it in this dimension here with the three-membered ring flat and in the plane of the phone or computer screen as you're watching this. And if you look at this isomer here, this also is a cis isomer. CIS isomer, okay? So if you have an alkene, the oxygen is delivered from the same side of the alkene, either from the top face or the bottom face, and it could possibly give you two different isomers, okay? The thing to remember is that cis gives you cis. Let's see what happens when we have a trans alkene. So here's trans 2-butene. And if we treat this with metachloroperoxybenzoic acid, we will get the trans epoxide. So let's draw this three-membered ring in the plane of the computer screen here. And over here, we'll draw this methyl group coming out. Okay. And over here, we will draw it going back. Okay, so remember, trans, when you're talking about a ring system, means that the two groups are on opposite sides of the ring. And in this case, they're on opposite sides of your computer screen. So if you start with a trans alkene, you form a trans alkene, okay? I mean a trans epoxide. And this trans isomer has the enantiomer that's also formed. Okay, the enantiomer is formed, and that's a mirror image, okay? So mCPBA is great. You can take any old alkene that you like and transform that to your epoxide. Now watch out for stereochemistry. Sometimes you might be asked to draw it, sometimes not. It just depends. Here I will choose to just draw a simple line drawing, okay? So when you do this reaction, make sure you keep the same number of carbons. I sometimes like to place 2 dots on the pi bond and then 2 dots on my epoxide, and then I want to draw that epoxy group in between those 2 carbons. Here as well, we'd want to draw our 6-membered ring. There's a methyl group, so make sure you include that in your final product. These are the 2 carbons of the alkene. These are going to be the 2 carbons of my epoxy, all right? So just add an oxygen between those 2 groups, okay? So that's the basics of drawing the epoxide using mCPBA. Now, the second method is that we can make a bromohydrin and then react that to form the epoxide. So let's take a look at a simple example. Let's take butene. This is 1 butene. And let's treat this with bromine in water. Now, you might need to review this from earlier in chapter, I think it's 6 or 7. You want to place the OH group at the more substituted carbon. And you want to place the bromine, or chlorine if it's chlorine in water, on the less substituted carbon. Okay, I'm not going to review this chemical reaction. Now, the reaction happens trans. I specifically picked something that we wouldn't have to worry about that, but the addition is anti. Okay, so this right here is another way of just stating Markovnikov's rule. Okay, and anti-addition means you form trans if there's a ring system or a more complicated molecule. This is the simplest I could pick here. All right, so we're going to have the OH group right here, which is the more substituted carbon, and we're going to have a bromine right here on the less substituted carbon, okay? And this functional group right here is called a bromohydrin, okay? So it's a 2-step procedure, okay? You take your alkene, you treat it with bromine and water, and then in the next step, you're going to treat it with sodium hydroxide, okay? So let's draw the second step over here on a separate slide. And we're going to treat this with sodium hydroxide, and this is going to form an epoxide, okay? Now, how does this work? Let me show you the mechanism for this step. And this would be, step 2, right? So you have your bromohydrin, and you treat this with sodium hydroxide. So sodium hydroxide can deprotonate this alcohol-looking functional group here. And I'll highlight this bromine here in purple, okay? And what happens here is it spontaneously reacts, okay? So you have a deprotonation step. Now, this oxygen is a nucleophile, and remember that halogens are great leaving groups for SN2 reactions. So what's going to happen here is that the negative charge from the oxygen is going to attack this carbon and kick off the bromide, and that's going to give you a ring system. Okay, so remember this came from 1 butene, and carbon 1 and carbon 2 are now going to form the epoxy ring system, okay, with that oxygen. So that's a ring closing reaction, okay? So it's a 2-step reaction. This is how it looks like with a number of examples, okay? If you have cyclohexene and you treat this with bromine and then water, followed by sodium hydroxide, you will form the cis epoxide. Okay, cis epoxide. Now, if you have something like this, okay, and we also treat this with bromine and water, followed by sodium hydroxide, what will you make? Here, you'll also make the epoxide, but this is a transalkene. So you form the this is technically a cis alkene, so that's why you form the cis epoxide there. I just wanted to highlight that. Now this is a transalkene, so you're going to form a trans epoxide. Okay, I'll leave the hydrogens off. Maybe I'll just write CH3 and CH3 here. Okay, so trans makes trans and cis makes cis still. Okay. So you have your choice of reactants. You could use mCPBA, or you could make the bromohydrin followed by base. So let's see if there's some problems here in the book. Okay, so problem 14.14 here in the textbook says figure out what reagents you would use to synthesize the following epoxides. All right. And so basically, let me show you how to think about this. You want to identify the two carbons that contain the epoxy group, right? And you want to remove that oxygen atom from that. And then you want to create a carbon-carbon double bond between those two purple dotted carbon atoms. But you want to make sure that you maintain the correct stereochemistry, okay? If we draw the alkene here between those two carbons, we know we're on the left carbon, we're going to have a methyl group and a phenyl group. And we want to think carefully about the position of those two groups. The phenyl group here is on a wedge, and the phenyl group here is on a dash. So those are opposite one another. So in our starting alkene, we want the phenyl group on one carbon. I'm sorry, I didn't mean to draw it as a pH. We'll learn about that later. You want one of the phenyl groups to be on one side of the alkene and the other phenyl group to be on the opposite side, okay? So these phenyl groups are on opposite sides in order to have one wedge and one dash in the product. Now don't forget this methyl group here. That methyl group is right here. We'll draw it in and write Me, and then we'll draw the hydrogen, okay? So that is the reactant we would use, and we would use, I don't know, mCPBA. Either of the two reactants would work. Reactants, okay? Now, in B, we want to think about the same thing here. We want to take those two carbons, okay, and create a carbon-carbon double bond between them, okay? And now we want to think about where these two groups are, okay? So we've got a hydrogen that's on the same side as the cyclohexyl ring. Okay, so I'm just deciding to put them back that way because dash means behind, so that's why I'm doing it that way. You could do it the other way too, that's fine. And then wedge, there's a hydrogen, and then a wedge methyl. Okay, so I'm kind of looking at the alkene sideways if you wanted to think of. Okay, in molecule C, it looks very complicated because you have two different oxygen atoms. But remain calm and carefully think about which one is the three-membered ring. This guy right here is the three-membered ring, and this is the one you want to focus on. You want to remove this oxygen atom between these two carbons, and that's where you're going to have a double bond, okay? All right, so you're going to have some kind of molecule like that. You can draw the H if you want. You don't need to, okay? In molecule D, you want to once again examine carefully which two carbons contain the oxirane, remove the oxygen, and that's where you're going to have your alkene. If you look very carefully, you can see that this R group, right, which is part of the chain that comes back around, is on a dash, and this R group, which is part of the chain that comes back around, are on opposite sides. So we want to make a transalkene here, okay? So this could be produced from mCPBA reacting with a transalkene, and it might be kind of hard to draw. It might look a little ugly, but that's essentially what we need to draw, okay? We draw like that, and then we draw the requisite number of carbon atoms coming around. Well, that doesn't look too bad, does it? Okay, so, make sure you count your carbons if you need to. There's 1, 2, 3, 4, 5, 6, and then the 2 of the alkene. So 1, 2, 3, 4, 5, 6, and then the 2 of the alkene. So that's a correct carbon count. So that's how you do these problems. You remove the oxygen, you create the double bond. But the important thing I want to emphasize here that a lot of beginning students try to do is you don't need to draw wedges or dashes on the alkene. Okay? Why do we not need to show wedges or dashes? Because alkenes are completely flat. They're sp2 hybridized, they're trigonal planar carbon atoms, and they're flat. So since they're in the plane of the board, we don't need to show them coming in or out. When the epoxide reacts with that alkene, then it forms a tetrahedral carbon atom, which we need to use show stereochemistry for wedge and dash. Okay? So that's the basics. You've got the bromohydrogen route or mCPBA route to form cis epoxides or trans epoxides from cis alkenes and trans alkenes respectively. I hope this brief video gets you started. Thanks for watching.